Thank you, everybody who is joining us today for our BrightBuilt Home Lunch and Learn. Before we launch into the presentation and to get into the good stuff, I want to just go through a couple quick nuts and bolts and also do introductions of the team. We are going to go through the entirety of the presentation first and then take questions after. So if you have questions that come up throughout the course of the presentation, you can either make note of them or feel free to go ahead and type them into the Q&A sidebar in the Zoom platform, and we will be able to address them in order as we go through the questions at the end of the presentation. So let's go ahead and do introductions. I'm Parlin Meyer. I'm director of BrightBuilt Home. I've been part of BrightBuilt Home since we launched in 2013. As many of you likely know, BrightBuilt Home was launched initially as a sister project by Kaplan Thompson Architects. We have since become our own LLC and our own entity, but we remain fairly intertwined with Kaplan Thompson Architects. In normal times, we share an office with them in Portland, Maine, and we continue to be all part of one big happy family. So I'm going to hand it over to Jessica Benner for her intro real quick.
Hi, I'm Jessica Benner. I am a project coordinator and architectural designer with BrightBuilt Home. I've been working here for about 4.5 years. Audrey?
Excuse me, I'm Audrey Rolio. I have been with BrightBuilt Home for 1.5 years. I am also a project coordinator and designer at BrightBuilt. I worked to get my Passive House certification in 2011 and have been working in high performance ever since.
Hi folks, I'm Jay Sanderfer. I am the Director of Sales, and I'm likely the person who will be communicating with you first on this team. Welcome.
All right, so let's go ahead and I'm going to share my screen. I'm going to be driving the slides, so to speak. So when Jessica and Audrey present, they'll simply be cueing me to bring up the next slide. All right, so here we are. And despite the appearance of this image, this is in fact an actual structure. And this is in fact a photograph of the structure. This is the BrightBuilt barn, which some of you may know is the granddaddy of all BrightBuilts. It was the project that was done by Kaplan Thompson in 2008 that seeded the entirety of the BrightBuilt Home efforts. So that's an evening shot from the home back in probably 2009 is when this photograph was taken. So yes, welcome to the BrightBuilt Home Systems Lunch and Learn. We're very, very, very grateful for your ability to join us today, and we're looking forward to this presentation and discussion. So we're going to kick things off today by talking a little bit about the why. Why do we use the systems that we use, and why do we build the homes that we do? And one of the biggest underlying whys to the existence of BrightBuilt Home is to address this very pie chart. So if you look at this pie chart, it's a fairly simplified reduction of the overall global CO2 emissions, and it's broken out by sector. And as you can see, transportation intuitively is one of the biggest chunks. Industry, likewise, is the biggest chunk. But there's a substantial portion of this pie that's occupied by buildings. Small portion, about 11%, represents the materials themselves that go into building buildings. These, of course, are not just homes. These are all buildings across all sectors. But then a really big portion, second only to industry, is building operations. So it's really critical that operationally buildings are working as efficiently as they possibly can to help reduce this overall CO2 emissions factor that operations contribute to. So this is, like I said, a big reason why we use the systems that we use and why we're trying to address this question of building efficiency. Another reason on a more micro level, and certainly in an individual level, if you are a homeowner, is simply the cost of fuel. So 20, 30 years ago, it cost a lot less to heat and cool a house than it does today. This particular graph is a little bit dated. It's now 5 years old from its last data set, but it still represents what is the continuing trend in fuel oil and gas and other combustion fuel source prices. Obviously, right now in this snapshot in time where we are in the midst of a pandemic, we're seeing some of these numbers fluctuate a little bit, but the expectation, of course, just in terms of resource availability, is that these trends will continue up. So from a personal standpoint, from a homeowner standpoint, investing in and using systems that are more efficient is wiser from a bottom line. So in conjunction with these increasing combustion fuel costs, logically, are also increasing electric costs. Obviously, a lot of the electrical plants, the production plants where electricity is produced, are using those fossil fuels and combusting them in order to create electricity. So it stands to reason that their costs would be going up as well. But it also makes a very strong case for when we're using electrical-based or electric-powered systems that we do, that we also generate the power that we'll need to run those systems on the site itself, thereby reducing our output for paying for electricity. So the third leg of this three-legged stool is the decreasing cost of solar panels. So just 10 years ago, 2010, the cost of solar panels was 5 times what it is today. So this continuing trend in the decreasing cost of photovoltaic panels has really made our holistic approach that much more affordable, as well as going completely net zero and divorcing ourselves from reliance on fossil fuels all the more attainable and possible. So all of these things, increasing fuel and electrical costs, decreasing PV, are what makes the BrightBuilt pretty attainable. So as most of you also are likely aware, we dwell primarily in the realm of using offsite and specifically modular construction to build our homes. Those homes are, generally speaking, divided in anywhere from 1 to 4 boxes, typically, from our smallest sidekicks to our largest Vinyl Haven and Acadia design homes. As such, within the boxes themselves, we honor what's called an air barrier. So you can see this red line that's drawn in this drawing here. And that red line in each of the 2 scenarios delineates where exactly the air barrier is. In the case of the illustration on the left, it is across the ceiling of the 2nd floor, and the attic would then be unconditioned and outside of the conditioned space, the thermal envelope, and outside of the air barrier. In the case of the illustration on the right, the air barrier includes that attic space. So it really is just dependent on the design and the pathway that you choose as to where exactly the air barrier lands. But that air barrier is important because it has bearing on the entire holistic system of the entire house. So we're talking primarily about mechanical systems today, but we can't really do that without at least mentioning the fact that the house itself is a system unto itself. The envelope of the house is as critical to the performance and the efficiency of the overall home as the mechanical systems are. So in our case at BrightBuilt, we use a 2x10 double stud wall assembly that we dense pack with cellulose. So we get that to an R40 nominal R value on the walls. The foundation and the attic then are R20 and R60 respectively. So we're really following the principles of R20, 40, 60, which is fairly widespread in the high performance community as the benchmarks for a very efficient home. We, of course, as was shown in the last slide, we also pay very close attention to the air barrier. So the continuity of that air barrier is really critical, and the air barrier in conjunction with the R values is what makes that envelope as robust and critical to the overall holistic performance of the home. Also, the windows and doors as part of the envelope are just as important. We want to make sure that all of our windows are triple pane, and by and large, we do either triple pane casements or triple pane tilterns. Casements or awnings, I should say, or fixed. and tilt turns, which are the European style windows that open into the space as opposed to casements and awnings, which open out. In both cases, those window types and that type of window operation creates the best seal when the window is closed and in its closed and locked position. So as opposed to a double hung window where you have a strike rail, where there's a lot of air seepage through that gap between the two sashes, these types of windows are able to lock in and seal really effectively when they are closed. So then the last piece of the envelope is ensuring that all of our projections and all of our all the modeling that we do to anticipate the performance and the load requirements for the house will be what we're expecting them to be. And so we do a blower door test. That's what you see in the right-hand image. That's somebody doing a blower door test. That's the contraption that goes into the door, hence the name blower door. And then there's a fan that induces negative pressure within the house to try to force air into the various gaps and cracks that there could be. Ideally, there are relatively few of them, in order to ensure that we're meeting the level of air sealing that we're after for the performance of the home. So that piece is just as important as the mechanical systems themselves. And in the case of BrightBuilt and in the case of many high-performance homes, these are the three systems that work in conjunction to heat, cool, ventilate, and provide hot water to the home in question. And all of them use extremely efficient technology in order to operate. So air source heat pumps provide our heating and cooling for the homes. HRVs and ERVs generally provide the ventilation for the homes, and heat pump hot water heaters provide the domestic hot water. So when you combine these elements, the robust envelope that's air sealed and tested with these really efficient mechanical systems, you get a net result of a home that performs substantially better than the same exact home built to code standard and using standard mechanical systems. The reduction is generally greater than 50% in load requirements for the combined heating plug loads, for the electricity requirements for the house, for things like computers, televisions, electronics, etc., and hot water. So these two things in combination, these two approaches in combination, are what contribute to the level of efficiency that we are driving for with our homes. And again, those two systems, the wall system as well as the mechanical systems combined, when you add renewable energy, you can very easily get to net zero. So that means you're producing all of the energy on your rooftop that you actually need to run your home for the entire year. Okay, so now I'm going to jump into air source heat pumps. These are the systems that many people are becoming more and more aware of. They're now being used pretty widely in retrofits or to add heat or cooling to given spaces that have older, dated systems that might not be as efficient. In our homes, they provide the entirety of the heat and cooling for the most part. But they are the core heating, cooling systems for the homes. In this image, you can see the mini split unit mounted on the wall on the right-hand side. And that's what most people think of when they hear the term mini split or air source heat pump, that's the unit that's widely used and widely recognized. So how do they work? Well, quite honestly, they work through somewhat simple but also somewhat complex principles of thermodynamics, which I'm not going to get into the detail of describing right now, in part because I'm not quite qualified to do so. But in essence, they work through a series of extraction, compression, condensation, and expansion. And in layman's terms, or to simplify that, essentially what it means is that they move heat from one place to another. So in the winter, when the interior spaces want to be warmed, the air source heat pump extracts heat from the outside air and moves it to the inside and delivers it. Vice versa in the summer, where it'll extract heat from the inside air and move it to the outside in order to cool the interior spaces. So this is exactly why these particular systems are substantially more efficient than their furnace counterparts because they move heat from one place to another rather than combusting a fuel source in order to create heat. So the people talk about, when you get into the finer grain of some of the specifics of these systems, you will hear the term coefficient of performance. Coefficient of performance is a rating that's applied to a given system to describe how many units of energy put in are then output and translated to units of heat. In your standard baseboard electric style unit, the unit of energy input is 1, the unit of heat output is 1. So it's a 1-to-1 system. Combustion fuel furnaces are actually usually less. So it'd be 1 unit of energy in and somewhere in the order of 0.7 to 0.9 units of heat out. In the case of these air source heat pumps, the coefficient of performance is generally in the neighborhood of 2.6, which means 1 unit of energy in generates 2.6 units of heat out. So already we can see we're at 2.5 times better efficiency than we could get in even the most efficient combustion-based or electric-based type system. Likewise, because they're electric, we can power it with renewables, as we noted. So there are 2 types of air source heat pumps that you can install in your home. One is the ductless system. The ductless system is the system that generally people think of when they think of these systems. It's the wall-mounted cartridge on the wall. It can also be available in a ceiling mount or a floor mount, and it's directly tied to the outdoor compressor. So that loop goes back and forth between the 2. There's no ducting. It can go straight through the exterior wall and connect directly to the compressor. It's a very simple system, generally requires very little to rough in. Alternately, we have the ducted systems. This is, of course, what is more readily recognizable to many people when they think about air-based heating and cooling systems, where you have a system of ducting throughout the house that delivers air to each individual space. And in this case, there's also a requirement for return air grills so that air can be extracted from the house as well, sent back to the system so that there's an overall balance in the circulation, delivery, and return for the ducted system. So likewise, you can do diffusers in the walls, you can do diffusers in the ceilings, you can do diffusers in the floors. Some considerations around the ducted system are really giving some good thought to where you want those return air grills to go. Those are generally larger than the standard delivery diffusers. So they can be pretty big, and it's important to think about where you want to place them. Oftentimes they're placed in ceilings of hallways where visually they won't really impact your day-to-day life. And then the other consideration, of course, is the ducting itself, where that's going, how it's going to get from floor to floor, where it's going to tie in with the main unit. The technology itself, though, in the case of this approach, is the exact same as it is with the ductless system. You've got an outdoor condenser and compressor connected to an interior unit that is delivering the heat or cooling to the spaces. So pros and cons, I think, probably are somewhat intuitive based on what I just went through, but to just go through some quick bullet points. The ductless systems, it's a fairly straightforward rough-in, simple system, no ducting required. As such, they're generally much more affordable than the ducted systems. And you can do, for our homes, with the envelope that we have, the R values and the air sealing that we incorporate, we can absolutely do just 1 cassette per floor, and that is more than ample to provide the required heating and cooling loads for the house. Some of the drawbacks to ductless, though, might be that it is a single point source. So if you don't have an open living concept in your first floor, or if you have a lot of rooms broken up and you want to deliver even heat to each of the spaces or even cooling to each of the spaces, it's an important consideration to think whether that single head will suffice for your needs. Certainly, it will have the capacity to heat and cool the entirety of the space. If you have a space that you want to have the door closed all of the time, you might give consideration to either a backup source of heat or cooling for that space, or possibly a ducted system. You're not going to have a dramatic enough temperature drop with those separated out spaces to be uncomfortable, but you may see a noticeable difference between that space and the other if it's completely segregated out from the rest of the space. There are other things you can do besides backup heat or an additional head to mitigate that, vis-a-vis transfer fans or undercut doors to allow for air movement between spaces. Another thing that's important to be mindful of is that multiple heads off of a single outdoor unit, so if you take multiple heads and you tie them all to one outdoor unit, you are likely to see an efficiency drop in the overall performance of the unit. So you might get down to more of the 1 to 2 realm of a coefficient of performance, or in extreme cases at 1 or below. So it's important to make sure that the system is designed appropriately for the efficiency that you're looking to get out of it. And then one drawback for some people is the aesthetics, that they don't like the big cassette on the wall. They don't like the way it looks, so they'd rather go with a ducted system to have the more simplified air vent grills that might be more familiar. For the ducted system then, as counterpoint, the pros are that they offer good distribution to the different rooms. You can get more of an even distribution. So if you do have that circumstance where you have one room that's fully separated out from the others, it's going to get the same air delivery as the other spaces. If you're doing a retrofit, you can use a ducted system to replace an existing system fairly easily. And then they do, because they're delivering more expansively to the entire volume of the house, you can get closer to that maximum efficiency of the COP of 2.6, although I will say the ductless units also are very capable of getting to 2.6 if you're doing a 1-to-1 style installation. The cons for the ducted systems are that they are generally more expensive. You have a greater capital upfront cost of the system installation by virtue of the ducting and the unit sizes themselves. And then of course the return air grills, as I already noted. So I'm going to now hand over to Audrey to talk about our next system, which is ventilation.
Hi there. So all high performance homes, oops, we can go back a slide.
Sorry.
That's okay. Other way, that's good, thank you. Thanks, Parlin. High performance homes, we want to add mechanical ventilation. Humans all like a good indoor air quality. And with the addition of mechanical ventilation, we have a controlled, purposeful, and filtered air that comes into our home. It also extracts pollutants from our home, including moisture and stale odors. As you can see in this slide, from the left to the right, the unit is the box in the middle. This is inside our home. This is in the basement, typically. The unit is either attached to the wall or to the ceiling. Inside the unit, the diamond shape is the core. It's a heat exchanger. And you can see the airflow through the exchanger. The gray bar to the right of that unit is the exterior wall of the home. And so the unit is placed on the exterior wall. And there are two outlets. Well, there's an inlet and an outlet on the outside of the home. One is bringing fresh air into the home, passing over the heat exchanger, and that is supplying our living rooms and bedrooms. Alternately, air from bathrooms and kitchen are being extracted, goes over the heat exchanger, and exhausted to the outside of the home. Next slide, Parlin. Thanks. You've probably heard that there are heat recovery ventilators as well as energy recovery ventilators. They both supply fresh air and extract stale air. The heat recovery ventilator has a core that's made of a ceramic material. In the wintertime, when we are warming up our air on the inside of the home, the extracted air, the air that's leaving the bathrooms and the kitchens, is warm air. That heats up the core on the way out. And then likewise, the incoming air passes across that core and gets tempered on its way into our homes. So it has that preconditioning element to the heat recovery ventilator. The energy recovery ventilator does all of the same things. its core is made of it's typically a filter material, almost like a paper. It can handle humidity. And so when air is coming into the house in the winter, we typically have a warmer and drier interior air. It can bring in some humidity to our air, and it lets the humidity stay. So it actually can help with static in the wintertime, which we often experience in code-built homes. It also, in the summertime, likewise can extract humidity from our interior air and not let it pass through from the outside. So we do have that seasonal tempering with energy recovery ventilators. Next slide, thank you. So what's inside the ventilators? We can see the core in the center of this unit. That's the diamond shape. Again, from that first slide, we have air passing through that core on both the intake and the expelled air. There are there's fans, of course, that are bringing that air in and allowing that air to pass outside of the home. There are filters that can keep pollutants from the outside out from our air. That could be pollen, it could be transportation, pollutants, anything outside that we do not want in our interior spaces. The filters are very important to maintain and to clean as often as necessary. And it's a very simple cleaning. Some can be cleaned as is, some can be replaced when they get to be too worn. And of course, there's 4 duct ports. There's on this unit, you can't see them, but there's 2 on either side of this unit. Next slide, please. Thanks. Here is a BrightBuilt Home energy recovery ventilator. This is mounted to the ceiling of a basement. That is the exterior basement wall that you see with the silver lines of tape. The ducts are insulated. That's what you see up on the ceiling. The 2 on the right side, they're both going to the outside. Again, there's 2 grills on the outside of the home. One is taking in fresh air and one is expelling the stale air. And then on the left side of this unit, one is a supply for, again, the living room spaces, the bedrooms, and one is an extraction from the kitchen and bathrooms. Next slide, please. Thank you. Those 2 units that I just described, the energy recovery ventilator and the heat recovery ventilator, they are centralized units. They have ducting, like we saw in the slide, throughout the home. It's a whole house ventilation system. When we design smaller units, especially our Sidekick, which is new, we use a different system. First of all, it's great for efficiency of space. And these units are called Lunos fans. Lunos fans are decentralized. They require no ductwork at all. They do work in pairs. So you see one of each here. And of course, they're great for smaller spaces, like I said, our Sidekick. From the square plate that we see going backwards, that square plate is the inside portion of this system. So that's what you see on the wall. Typically, it's on the about a foot from the ceiling. Just directly behind that, there's a white square with a red, round, black filter. That is a filter. Very easy to pop that cover off and clean those filters. I had this system in a house that I designed and absolutely loved it. Behind that filter, you see the fan. Each unit, again, has a fan. Behind the fan is a ceramic core, just like the just like the heat recovery ventilator that we saw in the previous slides. And then there's the grill that goes on the outside of your house. Typically, with a Lunos system, you are putting them either on opposite sides of the home, or at least where you want the air to flow through your home. So in a sidekick, it could mean end to end or something close to that. These fans work in concert with each other. One is bringing in while the other is extracting, and then about a minute later, the fans reverse and they go the other way. The one is extracting and the other one is supplying air. It's a fabulous little system. Next slide, please. Thank you. In addition, we do add exhaust-only fans to our bathrooms. And in our kitchens, we suggest either a kitchen hood that has low CFMs, typically 300 CFMs or less, or you can do a recirculating hood in the kitchen, which has no extraction of air and just has filters in it. Either way, kitchen hoods are very important to clean filters, as those filters are trapping particulate that is created when we're cooking. And we want to make sure, of course, that all pollutants, being moisture in the bathrooms or particulate matter in the kitchen, as well as stale air, odors, get extracted from our homes. So if we had a client that wanted a CFM that's greater than 300, let's professional hood, for instance, we would have to add a makeup air system. Typically, we'd put that in the basement of the home, and that just helps the balance of, we're not extracting too much air that we're bringing in, so that just adds to the mix. So we can do hoods that are higher than 300 CFMs, but most clients do find that 300 CFMs or less works for them. Thank you, Parlin.
Okay, on to our next system.
The next system is the heat pump hot water heater, and this is an image of one installed in a BrightBuilt Home basement. So you can see it looks very similar to your typical electric resistance water heater, but the difference is that it uses the same air source heat pump technology as Parlin had described for the mini split systems, and that is that it draws air, extracts the heat, essentially moves the heat from the outside air and transfers it to the water. And therefore it operates with the same relative efficiency as the mini split systems as well. So 1 unit of energy produces approximately 2 to 3 units of hot water or heat to heat the hot water. Next slide, please. So a couple of considerations for heat pump hot water. I commented on the efficiency, and we often locate these in the basement of BrightBuilt homes. BrightBuilt homes, as Parlin initially described, often come with a full basement or a crawl space. So if the mechanical room is located in the basement and enclosed in that space, because the heat pump is drawing inside air, not exterior air, it's drawing heat from the interior, the volume of air needed needs to be considered. So that space needs to be about 1,000 cubic feet. Also, because it's drawing inside air, the interior temperature of that space generally drops from 3 to 5 degrees. So there's another consideration. And likewise, because it is extracting heat from the air, it also acts as a dehumidification. So it dehumidifies the space that it's in. Next slide. And lastly, solar power. So solar is the sort of final component into achieving net zero for the whole house as a system, as we discussed. 100% of BrightBuilt homes to date have been grid tied. So the solar array is installed on a south-facing or southwest-facing roof. The solar panels generate power and are fed into the grid. The home uses what it needs, and if those panels generate more than what the home needs, then there is some sort of credit from the power company that is provided to the owner. Next slide. So a couple considerations for solar power in general, that is the size of the panel and the wattage involved in the panel. This graph indicates in 1954, the panel was 65 inches by 39 inches in size, and it generated about 20 watts of electricity, which translates to a third of a 60-watt light bulb. As you can see, over the years, the technology has vastly improved. So for the same size panel, 65 inches by 39 inches, the panel can now produce 320 watts, or in some instances even larger. The cell technology is really what's driving that. In residential applications, you'll see any panels anywhere from 280 to about 350 watts per panel. And that really matters because of roof size. So you have a panel that's 65 inches by 39 inches, and the more watts it produces in that space, obviously the more power it can generate for the house. So if you have a small roof, wattage really can matter. Another consideration for that is that the higher the wattage, generally the more expensive the panel. So generally in the 300s, panels can be a bit more expensive. Next slide. And then also, this is a snapshot of what we generate for our homes at BrightBuilt, and there's a lot of information on here, but we call this our energy model, and what it does is it crunches all of the data of the house, so number of occupants, amount of electricity used by those occupants, the systems, passive solar gains, types of windows, etc. And what it does is it takes the watt per panel generated, and it calculates the usable square footage on a roof, and tells you approximately how many panels the house will need to install. So for instance, this house will need approximately 7.2 kilowatt capacity PV array system. That means 28 panels on the roof. For BrightBuilt homes in general, we're seeing a range of PV size needs. So that can range from 4,000 kilowatts, or 4 kilowatts for the sidekick, and about 10 kilowatts or less for the Vinyl Haven in Acadia, which is a range from 700 square feet to almost 3,000 square feet. Next slide. So we started this presentation with the why we're doing what we're doing, why we're so invested in both the envelope and the mechanical systems, and that is the cost of fuel and reducing CO2 emissions. And really, high performance is meant to improve the building sector. So in this illustration, in this table, you see a proposed BrightBuilt project and all of the R values associated in comparison to a code-built home, 2009 compliant home. And what you get is the difference between the yearly heating demand in kBTU per year, and you can see that it's almost a third. A BrightBuilt home is almost a third of what the code-compliant house needs. Likewise, further translating that to a comparison of heating costs between a high-performance BrightBuilt home and a code-compliant home. So this graph is from a couple of years ago, so it reflects the prices of a couple of years ago, but across every fuel type, you can see that Due to the nature of the envelope and the systems used, the cost to operate that home is substantially less, ranging from 30 to 50%. And then again, sort of a comparison of energy use, taking it further to older existing homes versus typical new homes versus a BrightBuilt home. A graph to illustrate sort of the totality of what's needed to operate the house, the space heat, the electricity, and the hot water all together is a substantial reduction. Next slide. And lastly, what that translates to for a homeowner is monthly costs. So in this graph, it illustrates the cost of, we'll call it a mortgage for a code-built home and a BrightBuilt home, and then the operational costs altogether. They're substantially less in a BrightBuilt home, which means that those funds that you would typically spend on a monthly basis can be sort of funneled back into the quality of the home that you're building. And you, in doing so, you even end up with a small amount of savings. And so you're happy and it's free. And that brings us to the end of our presentation. Thank you.
Great. All right, so we do have some great questions, and we can go through them one by one. I think maybe I'll read them out, and then the respective topical presenter can respond to them. The first question is from Dave, and he asked, regarding the house envelope, is there an alternative available instead of the 2 inches of polyiso rigid, something with a lower embodied energy and more environmentally benign? So I'll go ahead and just answer this one quickly because this is from the initial section. And I will say, Dave, you are very astute because you picked up on this detail from what is actually an old diagram. So you saw the 2 inches of polyiso in the here in this image. We have in fact changed this since this diagram was done, and we do exclusively dense packed cellulose for exactly the reasons that you described. So to reduce the embodied carbon in our wall assembly, and also reduce some cost for the assembly. So we had to use this assembly in our early days because of some of our earlier modular partners, but we've been able to since go with a full true double stud wall assembly. So thank you for that question. Second question is from Paul, and this is for Audrey. It seems obvious that HRV and heat pump, well, actually either of us can answer this, but it seems obvious that HRV and heat pump should be combined in one system. But at least as of a couple years ago, I couldn't find any product like that. Does someone make a good HRV ERV system that incorporates a heat pump to heat and cool air? Would you like to take this, Audrey?
Sure. Yes, that is a very good question, and not that I am aware of in the States. It does make sense that you've got the ducted systems. You should be able to pass air and heat together, which you do, of course, with the ventilation. But I suspect early, and I might be wrong, Parlin, jump in when you need to. I suspect that performance might be an issue with both of them being combined. I do know that in Europe, they have magic boxes that like, it is a unit that does everything, including heat, hot water. It takes up considerably less space. It makes so much sense, but I don't believe that the US has given its thumbs up to any magic boxes. So yeah, I think there's some room for that. What do you think, Parlin?
There are some manufacturers that are trying to make inroads right now. It's certainly not a product that is widespread, and finding an installer or finding someone who could maintain the unit would be a challenge in the current marketplace. You will find some installers of these systems who are willing to combine them, but it's in our experience and in conversations with mechanical engineers, it does tend to make an impact of a somewhat negative impact at to the maximized efficiency of both systems, as Audrey was saying. So if you wanted to combine them into the same ducting, you have to be mindful about the impact that would be made to each of the individual systems. But as a proprietary system, Audrey's absolutely right. There is not yet anything that's widespread in the market in the United States yet, unfortunately, but hopefully soon. Okay, our next question is from Catherine. Typically, how often do filters need to be cleaned or replaced on ERVs and HRVs?
Yeah. And that really depends on occupants and usage. It depends on so many different things. And so what I suggest to homeowners is that, you know, when you first move in, I would suggest looking at the filters even as much as once a month, just to see what you know, gauge what your use is like. If you are a family that has lots of open windows and lots of things just keep being left open, like doors all the time, you may have some influx of pollen that you might need to filter out and clean those filters more often. But it really depends on your usage. And likewise for kitchen exhausts, because, you know, I think this doesn't specifically mention ERVs, HRVs, but likewise for kitchen hoods, those filters for kitchen hoods, they can gum up pretty quickly if you do a lot of heavy cooking. And, you know, blackened fish or fried this or that really depends on your usage. So it's super hard to say how often. It really depends on usage and the homeowners. I see the next question from Paul. It says, but the Luno system abandons any heat or energy recovery. Yes? No. Remember back at the slide, we had the core of the ERV, the Luno CRV, right in the center there. That is about, I would say, 4.5 inches long, and it's just a big ceramic core with all these holes in it. That does essentially the same thing that the heat recovery ventilator does, where in the wintertime when you're extracting air, that core warms up, and so therefore when that Lunos turns around and is then bringing in fresh air from the outside, it is pre-tempering. It's a smaller core, of course, than the big Broan or Venmar or other manufacturers, but it essentially does the same thing. Interestingly enough, HRVs have, heat recovery ventilators have a condensate drain that will drip out moisture that it retains. These do not. So I can't say if these are called energy recovery ventilators or heat recovery ventilators because of the core. I would say it's an HRV.
Yeah.
I've lived with these systems for a number of years and had a high performance home that I designed, and I can say that I never felt any static or anything like that in the wintertime. I didn't feel any difference moisture wise with these systems as opposed to an energy recovery ventilator. I can say that depending on how you live, if you have a partner that opens all the windows and leaves all the doors open in the summertime, that moisture is coming in. So it was always better to shut the windows and let the ERV, the Lunos, do its trick. So again, usage is important.
Okay, and then the next one is also an air quality question. Do you recommend air quality monitoring given the tightness of the envelope / reliance on ventilation, i.e. in case the ventilator stops working for some reason?
Well, I guess I don't know what air quality monitoring means, but I think I'm going to have to work on or ask Parlin to help me out on this one. I'm not sure. I mean, I've used monitors in other regards in wall systems, but I can't say that I've used anything in the home. Maybe just a temperature gauge, is that? I'm not sure.
Well, an air quality gauge, so there are some systems out there that do integrate air quality monitoring with the performance of the system. So it does depend a little bit on the system that's installed. But that said, in the years that we've been operating, we haven't seen or heard an instance of the systems. We haven't had an instance of indoor air quality being so detrimentally affected that it's a problem. So even if the system stops for a little while, or there are other conditions that have to be mitigated, it can be dealt with. You're not in a hermetically sealed box that's going to remove all oxygen. So it's not necessarily a factor of safety. So it hasn't been something that we've incorporated into our homes as a monitor, though it certainly could be if it was a concern. Okay,
so I can see the next one. I'll just read that. Dave asks again, are the recirculating style of kitchen hood less expensive and simpler than the ducted style? Explain the differences. It's interesting. In the past couple of years, I've noticed that recirc hoods have gained in popularity and style. When I first started doing this work, they were typically kind of squat units and not very attractive. And I think that the industry is coming up to speed and giving people what they want, a nice looking hood, and the ability to either have it as a recirc hood or an exhausted hood. Price per unit wise, there's not much of a difference. And I think that literally the units that can go either way, it might be literally just a switch. However, there is ductwork for an exhausted hood. And so putting the ductwork in does require more work on site, and it does need to be exhausted to the outside. So there's ductwork in your kitchen wall, and then outside there's some kind of a vent on the outside to cover that up.
Okay, next question is for Jessica.
Joy asks, what is the future of solar panels and how soon would you consider using different materials, for example, solar shingles? I'd say personally, the future of solar is pretty exciting. I think that there is a lot that's being innovated currently that will just continue to improve the technology. Certainly over the last 70 years, we've seen some substantial both efficiency upgrades and cost improvement in cost. As far as solar shingles or solar roofs, we have yet to have a project that explores that, although we may have one in the works currently. We do have a couple of clients who have tried to explore that, and what ends up happening is that it really is cost prohibitive at this point. As far as I know, there's been a lot of positive reviews for those newer technologies, but they're just, they continue to be cost prohibitive.
I'll add to that too, that I think the one that's gotten the most fanfare, the solar roof from Tesla, is not yet available. So while their marketing is very enticing, the technology is not available yet. All right, so the next question is, if a house is built on a slab, where do the mechanicals go? Is that is the next question, yes, okay. I'll go ahead and just jump on this one, and that is a couple different places potentially. Generally speaking, if the home doesn't have an occupiable attic space, or the attic space is not within the thermal envelope, then a mechanical room is generally accounted for in the design of the home. One consideration with this scenario is whether or not you still go with the heat pump hot water heater. As Jessica noted, those require a minimum of 1,000 cubic feet to operate efficiently. And so unless your mechanical room is roughly 12 by 10 by 8 or 9 feet, then you'll likely want to go with something slightly different. You could go with an electric resistance that's super insulated, so it's more efficient than a standard electric resistance, or something else in order to generate your hot water. So yeah, so you have various options. The other option, of course, could be to build out into the attic bay or the volume, air volume of the attic for those systems. Certainly we've done that on various projects in the past where it's been a slab-based project. Generally speaking, with BrightBuilt homes, we build on either a crawl space and typically a full foundation basement, because when you're building modularly, the modules come together and you need to be able to get up underneath them in order to make the connections between the modules. And then in addition to that, the floor structure is already built off-site, so to have it sit down on top of a slab would be redundant. So for BrightBuilt's purposes, we are almost exclusively building with crawl space or basements, so the mechanical space is less of a factor in our designs.
Harlan, someone also asked in relation to that, for instance, a high water table on a property, how high of a crawl space walls are needed to fit HVAC within that space?
Great question. There again, we can fit just about all the systems in a standard crawl space, which we consider about 4 feet deep. However, the heat pump hot water heater they're generally tall, skinny units. So those would be up against the same constraints that you would have as a slab. You'd have plenty of air volume, but you wouldn't in this case have enough height. So you would again want to go with an alternate hot water source in the instance of a crawl space where you can't install a heat pump hot water heater. So 4 feet should be more than ample for the other systems. And we could get creative with designing for a heat pump hot water heater if that is desired. Next question is, why are so many vaulted ceilings in our designs? Isn't that energy efficient? I think in historical context, that was understood as being fairly energy efficient because the homes, traditional homes, co-built homes, any home that anyone has generally spent any amount of time in the winter in New England has a heat gradient whereby the heat moves from bottom to top and generally gathers at the top, and then you have to keep pumping heat in to make up for that movement of air. In a high performance home, however, the gradient is far more even and not stratified. So we've had clients refer to it as surround heat, whereby you don't have that classic experience of really cold feet and a warm head, or cooler at the floor and warmer at the ceiling. So vaulting actually is not problematic in a high performance home because you're really retaining so much of the heat that you're producing, and thereby you don't have a lot of heat loss in an upward motion, and you don't have to create, make up for the vacuum that gets created in the heating system as a result. So we're really, in the instances where we're vaulting, we're trying to take advantage of air volume that we already have within the envelope, within the roof, and gain that extra square footage as a result. I'll throw, I know this is a general one, but Audrey or Jessica, you guys can answer this next one. How is the basement floor insulated? And have we ever included geothermic heating? You want to take that one, Jessica? And then you can bounce back and forth.
So the basement floor is insulated with rigid insulation, and that is insulated to about a nominal R20. We have never included geothermic heating in our designs or the design of the system, and that is largely due to cost associated. And also just there, in our minds, there are more efficient systems available, more accessible systems available.
Before going to Gary's next question, I'm just going to interject to say we are just past 1 p.m. now. We'd originally suggested roughly an hour for this presentation. We will, I think, have time to finish out the remaining questions. So those of you who are still with us, feel free to stick around. We'll continue to answer questions. But just as an aside, we will be making this entire presentation recorded and available to all participants who signed up. So we'll be emailing a link essentially to view the entire presentation if you have to step away and want to follow up with the remaining questions at a later date. Okay, so I'll go into the next question. Oh, I see. So the new ones are coming in up top. Are there residential wind power options? Anyone? I can answer it too, I believe. How about I give an answer, and if Jessica or Audrey have a better one, they can jump in.
Okay.
To my knowledge, yes, but not really. So you certainly could set up a wind turbine on your property and have it generate power for you. How exactly you engage with that power or how it ties to your panel would depend on the way you set up the system and perhaps the expertise of your electrician and their familiarity and comfort with bringing in an outside source. To my knowledge, the way you would have to do that would be to power a battery bank and draw specifically off that battery bank. I am not aware of any readily adaptable wind power sources that can be grid tied. So, the short answer is yes, it can be done. The longer answer is it's complicated. So I'll stick with that. You guys have anything to add?
No, you did a great job.
Okay, thanks. All right, next question. Similar to Jack, how do you monitor to make sure there's enough breathing going on in the home and no mold potential?
So that's a great question. The systems are designed for the volume of air in your home. So whatever your volume is, the systems are designed to that. We don't do any monitoring. However, you can definitely, well, you can be rest assured, most of the mold comes from, well, often mold comes from moisture staying in your home. And what the danger is with new construction and building it tight is if building materials contain too much moisture that they can't let it out and dry. And I think that as many of you may remember back in the 70s, maybe some of you remember, there were super insulated homes that were built, very thick walls, tight homes, but without ventilation. Those homes essentially molded right out. There was no way to mitigate that moisture. It just stayed in the home. With the ventilation, it's constantly moving. Materials are allowed to dry. We don't see any mold in homes that are ventilated. If anyone wants to add to that, you're welcome to.
That's good.
Okay. So the next question, yeah, I remember, thank you, Brendan. I remember Adam Cohen starting on a system like that. I don't remember what it's called as well. When I took my training, boy, it just, you know, when you're taking your training and you're learning from some people from Germany, it's like, wow, it's so much nicer when you have a unit that is doing the all-in-one. Why don't we have it here? And so, yeah, kudos to Adam Cohen for working on that. And I would say we could all take a look at that and see how that's progressing. It would be nice to be able to have an all-in-one system. Dave offers another question. What sort of filter is on the Lunos system? Looks like just a thin carbon fabric sort of material. Any specs on its effectiveness? I'd have to look up specs for its effectiveness. Having lived with one for 3 years, I can say that it's kind of a spongy, it's not plastic, but it's some kind of a material, filter-y looking. It almost looks like a very loose sponge, but it's harder in that regard. Super easy to take out, clean, dries very quickly. I think when you buy the Lunos system, they give you a set of extra filters, but if you're careful with them, you can just literally just keep washing them. I don't believe I needed to wash them any more than a couple months with my family of three in a home that was about 1,700 square feet. I had 2 systems in that home. And so the next question is also on the Lunos. What is the price on the Lunos and how much square footage can it cover? That's a great question. The price is about, I think our retail price is just over $1,000 for a pair. Does that sound about right, Parlin?
Yep. About
Yeah.
12. Yep.
Yeah, and so I mean, literally, that was what I paid in 2013 for the system for each pair. Excuse me. So in my own home, I had a pair on the first floor and a pair on the second floor, and so again, that was about 1,700 square feet, and it worked very well because it wasn't ducted. On my second floor, I had it at either end of the home, and those were 2 bedrooms on the second floor with an open loft in the center. I had the doors undercut to the bedrooms, and I also had a slot above the casing, door casing, that even if the door was closed, allowed the ventilation to pass, the air to pass. So.
All right.
Yep.
Maybe I'll send this one over to Jessica. She spoke about PV. So the next question is, what is the difference in cost between building a net zero home versus an off-grid home?
So the main difference in cost is going to be the battery, the cost of the battery itself. I actually don't know what they're currently, if either of you, Audrey or Parlin, have an idea of that, what batteries are currently running these days. And the way the house is, I guess, hooked up will change, but largely the bulk of the cost is in the battery itself.
Yeah, I don't know battery cost, but I kind of remember, if you're close enough to lines, it's better to tie in because of battery cost, and also that battery draining after a while. So yeah, I don't recall the cost of batteries.
My understanding is just a rough cut rule of thumb is that a typical, let's say a Tesla Powerwall, for example, I think is in the neighborhood of about $7,000 to $8,000. And what I've heard in the past is that to run a house such as the one we're showing here with full capacity for all the washer dryer, all the needs of a typical, 4 to 5 person, 2,400 square foot home, you would need on the order of somewhere between 7 to 9 Powerwalls. So you're looking at somewhere in the neighborhood of $50,000 to $60,000+ just for the battery bank alone.
Yeah, you can actually go to their test site. I mean, their website, and there's a you can plug in your stats, and it kind of comes back to you with a price. There's other Powerwalls, of course, but Tesla's
right. Yeah,
an easy one to talk about. Since Dave asked, since a Luna system does not have a moisture drain component to its design, does it suffer from moisture buildup in its channel? No, I've never experienced that whatsoever. I imagine I never had any moisture whenever I cleaned the filters or inspected it. Not at all. I think that there's probably some evaporation going on to the exterior with the Luna system.
They're also installed at a slight angle outboard, so slight angle up, so that any water, any moisture drains positively out to the outside of the house. So when you look at the installation requirements, it has a slight cant to allow for any potential condensation to just drip out of the unit and out down the outside of the house within the drainage plane. So it's probably mitigated in both ways, as Audrey said, through evaporation, and then also that's sort of the secondary stopgap. Next is, can you describe the tool that you use to customize your designs? How much architect work is required to add a room to a design, for example? Anyone want to take that? Or should I? Jessica, you want to answer that, or I can do it too?
Yeah, I can answer it. So we are, Parlin, myself, and Audrey are all architectural designers. We use a tool called ArchiCAD, or a program called ArchiCAD, to fully model the home both in 2D and 3D. And if you were to sign on for to build a design, you would be paired with one of us, and we would work through a process where we meet, we discuss your needs, and we amend one of our sort of base designs to meet your needs. And that means moving rooms, moving doors, changing windows, basically anything that's within the existing footprint size of the house.
Okay, I'll take the next question, which is from Stephen. Have you considered using slab insulation that's not rigid foam? Embodied carbon concerns and energy problems such as with the polyiso, for example, foam glass. I can say, Stephen, that philosophically and functionally, I guess, we would very much love to use an alternate to foam. But the cost is very prohibitive for the alternate materials that are currently available in the market. There are some materials that are somewhat approachable in cost, but their R values are so low that it doesn't ultimately make it worthwhile. And for the slab insulation, we do spec EPS, which is the extruded polystyrene, as opposed to the polyisocyanurate. Which does have better blowing agents and a lower embodied carbon footprint as a product. So we're still trying to do the best that we can with the products that are available at the price points that are available. But yes, it is something that we continue to strive to move away from, anything that has a higher embodied carbon or is in general less ideal from an environmental standpoint. But
and that being said, the general contractor who is in charge of your job and on-site work, you can discuss ICUs, insulated concrete forms, ICF, excuse me, or some other insulated basement, whatever works for your budget. Typically, it seems like for budget reasons, we go with what Parlin suggested.
Okay, and next is from Tracy, back to crawl space. How high to get a heat pump hot water tank in? Jessica.
I want to say that the average tank size for a heat pump water heater is about 5 feet tall. And then you'll need obviously a little bit of room to maneuver within that space, get water lines in and out and attach to drain lines, as well as elevate the tank itself above the floor slightly. So we can call that probably 5.5 feet minimum for a generous enough space to have the traditional heat pump hot water heater tank.
Yeah, and I would, if you were going to proceed into construction, I would just recommend investigating the unit that you think you might use, just to make sure that you have ample space, because they do vary. They can vary pretty wildly from unit to unit and capacity to capacity. Last question from Tim: typical cost per square foot. And I presume this is a general question about the homes themselves for construction, rather than something specific to the mechanicals. And there is unfortunately no such thing as typical in construction. And we also at BrightBuilt, we work from Maine to Virginia. So we also see a pretty broad range of costs in the different regions in which we build. In a very broad stroke, I would say $225 to $350 per square foot. And it very much depends on where you're building, what you're building, how big it is, what your site looks like, and what your finish selections are. So that's why it's a very difficult question to answer in general, and as to exactly where in that spectrum you might fall for a given project. Right. One follow-up question from Gary, looks like, to that answer that I just gave, which was, does that cost include solar? And again, my question, Gary, or my answer, Gary, will be general and broad and non-specific, which is to say it could, but it depends on where in that spectrum you fall. And I will say, generally speaking, when we do ballpark numbers for folks when they first come in and they're interested to see whether or not something they're trying to do is aligned with their budget, we do add a line for solar and what that anticipated cost would be. But generally speaking, we don't like to incorporate the costs for solar into our anticipated construction costs for a project, because we want the number that you walk away with for the construction cost to represent construction alone, rather than incorporating solar. The solar effectively represents 30 years of utilities. So if you were to shop around and compare numbers with other builders or other entities, and they didn't include the cost of the utilities to power that house, it wouldn't be an apples to apples number. There's also some variability from house to house and site to site as to the level of performance of the solar array itself. So exactly knowing what the size of the array will be is hard for us to know at the outset. So, so yes and no, that number certainly can include the cost of solar, but it would depend. So I think that is it for our questions. Thank you everyone for joining us today. Audrey or Jessica, do you guys have any closing remarks or anything to add?
No, but thank you very much for joining us. We got some very nice comments on our chat. Thank you very much for those. We enjoyed it.
We look forward to the next webinar.
Yeah, keep your eyes out. We'll have another topic rolling out pretty soon as far as the next one, hopefully within about a month. So thanks everyone for joining us today. And again, this will be recorded and sent out, so you'll be able to circle back if you had anything you wanted to revisit. All right. Have a wonderful weekend.
Thank you, folks.